Okay, so it's a great pleasure to have Professor Oh Jeongseok from Seoul National University, and he's going to talk to us about the pullback between sheaves on log Calabi-Yau foods. Please go ahead, Professor.
Yeah. Thank you very much for the introduction and invitation. And I apologize, I changed my title following Hyunjun's talk yesterday. Mm. Yeah. So as in the original title, this is about certain pullback, and yeah, we've seen like one pullback from yesterday Hyunjun's talk. Before I explain what it is, I recall a lot of local models of spaces. So let me begin with the -1 shifted symplectic space M. Then locally it looks like locally there is a smooth space U and a function f on U such that its critical locus is isomorphic to M. If we start with the -2 symplectic space, shifted symplectic space, then locally there is a smooth space and a quadratic bundle on V and a section of E satisfying this isotropic condition such that so original space L is isomorphic to the zero locus of this section. We consider -1 Lagrangian space of a symplectic space. Then locally there is all these U, F, and V, Q, and S, and a smooth map between these spaces. Satisfying this condition such that this Lagrangian morphism is coming from this morphism, and these are isomorphic to the zero section and critical locus. For example, any point is the critical locus of zero function on the point itself. So the point is -1 symplectic space. And if L is -2 symplectic space, then the trivial map from L to point becomes -1 Lagrangian of this point, which is -1 symplectic. Next, I will introduce an analog of Hyunjun's pullback yesterday. Yesterday, we've seen they constructed certain morphism between from DT cohomology of symplectic space to certain homology of Lagrangian. So this is constructible side of this pullback, and I'd like to explain what we can do in coherent side. This conjecture can be stated this way. So we have certain category coming from this -1 symplectic space, and there is a functor or map from here to yesterday. This is denoted by L, so I will also denote it by L. And choice conjecture says there is certain category assigned by M and a functor from this to derived category of L. Or maybe we can say there is homomorphism of their K-theory. So maybe there is K-theoretic version of this choice. There is this choice conjecture says K-theoretic version of this. So a certain abelian group to K group. This is choice conjecture. Yes, I'm consider yeah. So this stands for matrix vectorization, but we don't
function. So there is no function.
So yeah, that's why I said the conjecture says there is certain content.
So there's no function. MFK.
Yeah, I didn't define.
It's the gluing of the basic
Yeah, yeah. We can consider it as gluing of such representation, but since there's no successful constructions, I sense there's some.
So locally, that will be the position of
Yeah. That's.
I recall what we can do in -2 symplectic side or DT4 construction. So if we start with the -2 symplectic space L so let me consider the local situation. So let me assume L comes equipped with this smooth space and quadratic bundle and section with this condition. Then we have so now this is really matrix factorization, and we consider this is the total space of the bundle E, and the quadratic form becomes quadratic function on the total space of E. So this is really matrix factorization. So this isn't, although we don't know what it is precisely. So in this local situation, there is a functor from here to matrix factorization of zero function. But the support is the zero section on V, the zero section which is V, which means we consider only factorizations acyclic away from V. So this map is given by Clifford factorization. So up to this level, we didn't use a section. Then to using section, what we get is this commutative diagram. So now we have a map given by pullback of this section, then this gives a matrix factorization of V and QSS, which is 0. And here we also have a map, the restriction of this Clifford factorization. And the result is result lends to the factorization of V, but now the support becomes the zero section of S, which is L. So from this data, we get this commutative diagram. And here, we can go further. So if we take a cohomology, then we get an element of the derived category of V, but whose cohomology lies in L. Okay. And in this side, we get, there is an obvious functor given by pullback. So this pullback. This was denoted by pi. Then, yeah, so this is one example of this construction. So in conclusion, in this -2 symplectic case, and I mean, even in local case, we can understand what maybe this can be one candidate of this pullback. And the advantage of, or maybe the role of this pullback, or one thing we can see from this pullback is if we start with the structure shift of point inside here. Then it goes to actually this is for the audiences who knows this story. We have to consider some twisted things, which is now structure shift because this is point that goes to yeah, sorry. Maybe from now, yeah. That goes to the structure shift of V, actually with some twist. And this goes to this structure shift of V tensor with the Clifford vectorization. And taking cohomology, this goes to virtual structure shift over L.
What TL, T of L, the fourth line. Oh, one is T of L,
Where is the over?
the fifth, fourth line.
This?
Yeah, next,
So this conjecture says there is some category and there is functor.
what is TL, T of L.
This is derived category.
Right to L.
Yeah.
Now, let's consider Lagrangian case. So assume this Lagrangian is obtained by this local structure. So there is B, E, S, and there is U, F, such that QSS is the pullback of function F. And this is isomorphic to critical locus of F side here. And this is isomorphic to zero section, zero of this section, which is rising B. And from this, we still have all this story work. So we still have functor from the total metric factorization of E and coded function Q. And here we have functor. And also using the section S, we have B, and on this side, since this is factorization of zero, so this part it automatically becomes the function automatically becomes zero, and here also the support should be L. The only difference is now the function becomes non-trivial. And again, we obviously have this. By taking cohomology. And here we have pullback from UF to VF. So this is one candidate of again. Choice. So far, we have talked to only 4 local cases. So let me move to global situation. So again, let's recall what the idea of this globalization in DT4 case, or -2 simplex case. So in general, so this is a classical tool without derived geometry. In general, there is deformation from the ambient space to the normal quant. So we start with the ambient space, and you can find its deformation reaching to the normal quant of the zero section or space L inside V. So still, we assume there is this the triple V, E, and S, because I'm explaining the idea of globalization. I'm not explaining how the actual construction. So one important fact we have to use is this deformation lies inside the total space of E. And one line explanation of getting this deformation inside E is if we understand this ambient space V as a graph of our section S. So recall S was section from V to E, so its graph is isomorphic to V. Then this cone becomes the limit of this limit of graph of S divided by T. So and in algebraic geometry, it is well-known fact that if we have a family over a curve, so this curve is now the parameter space A1, and if this deformation is irreducible, then this is flat. So these two objects are somehow same in homology. Anyway, using then the idea of globalization is replacing this space V by the cone. So let's recall this diagram. So we had this diagram from factorization, matrix factorization to this. Yeah. Now, using this inclusion of the cone inside E, so we can define pullback to the cone. So now, if we denote it by, if simply denote it by just C, then the inclusion gives a pullback map from E to C. Now the intersection of, so this support becomes intersection of the C and zero section, which is gain. And what we can prove from the fact that it is limit of this graph, that this becomes zero. So even if we use the cone instead of a V, we still get this here C, and here and this. And what we can check is, so again, we can start with this structure shape of the point, and then we get certain element here. And what we can prove, this equals structure shift, virtual structure shift over L inside the A group of L, which is isomorphic to the K group of this category. Okay. And the point of globalization is we can glue cone to get some global space, whereas the ambient space is not glued. Hence, we use the structure shift of resulting gluing to define the virtual structure shift of L globally in K3. So we define it to be tensor of, sorry, answered with the Clifford factorization. And so to move on to Lagrangian case, so we remark this structure shape of the cone is the specialization of the structure shape of the ambient space. So yeah, these are the story already developed in DT4 side. Now, just taking
over because this is factorization of zero. So this is complex. The different the composition of differentials are zero. So we homologous makes sense. Okay.
So do we put it in degree 0 and 1, for example? Like, do we have to choose which degree?
Yes. So
So it's not a direct category. What is DL?
yeah. So it's homologized. Support.
So it's just a two-periodic complex, like an unbounded direct category unbounded. I mean, if the map is not taking homology, or I'm confused. If you take homology, then you get a sheaf, but you want some complex there. So
So maybe you need take this. I haven't so carefully, but need.
so it's not like a complex. It's like a just a
Complex with zero differential.
Yeah. But is it
a function? Yeah, I don't know.
it's a function?
Is it
Yeah. This is just a complex.
yeah,
homology.
Okay. Now, I want to consider global case.
Although the E is not good, but so application at
Sorry.
in the definition of preferential structure, you
Mhm.
all have L. Is defined to be all have going of C.
Yeah.
And so this as E. So E is not
E. So yeah, I should say E is already somehow close. So E is actually, you can think of it as absorption bundle over L. So it is close. This global is not really global as we have seen hundreds of it's partial global, which means we still assume there is a
so M is local. We still assume M is local, but L is global, which means this morphism is Lagrangian. Of local -1 shifted symplectic. Then the difference. So now what we have is using that inclusion. We also have all these picture. So here now it becomes you see near this also C. this thing is this video is also C. But if you use and I should say this may not be, again, this may not be 0. The difficulty is we don't know how to construct this. The idea is using pullback to MF, we QSS, and construct specialization map from matrix factorization of V to the cone. So this is our main theorem. Let me rewrite it. It is our main theorem. The theorem is there is a specialization I should say it's an assignment from object of here to here, set map, so object of such that giving homomorphism between K groups. So start from K, U, matrix factorization of UF to okay. So we can check some property we have to expect, which is comparison and localization. So the statement of comparison is for any quadratic bundle. Now this is different quadratic bundle, any quadratic bundle Q on U, not V. We have -1 symplectic space given by the critical locus of this space and function. Now we are considering the total space of this bundle. and the function is pullback of f plus the quadratic function q. Then this -1 space is isomorphic to the space we already have. So this is as -1 space. Also, we know famous isomorphism between matrix vectors and categories called narrow periodicity. Between matrix vectorizations. This is equivalence between functors, between categories. But
Yeah, sorry.
Is map not factorial?
I haven't. So yeah, I haven't
Because
checked that this is
compare objects. But how can that be reduced to a group then?
what we can prove is if we start object, a single object here, then we can reach zero object here. That thing we can prove, and also show the exact sequence preserves this plus.
But in general, it's not factorial.
I haven't really checked because that's not our purpose, but I guess it's not a. So the construction is very geometric. So it's not easy to see there's space it becomes.
periodicity, which is
That's right. ANO. UNIST.
Yeah, Canary.
Name
It's
of
the name of person.
then the statement of comparison is it's K group of MF Q and F Q, which is isomorphic to K of MF of UF. And we've already constructed these morphisms, and the statement is this is commutative. Yeah. And finally, let me assume there is a torus section on this Lagrangian. Then the theorem says this is push forward by inclusion, and also this is push forward by inclusion. And here we have morphism. Here we have morphism LT. And the precise statement is these are commutative up to certain correction, which is the square root Euler class of a normal bundle of L inside UT. L inside U, not M. And the numerator, we have to put Euler class of a normal bundle of UT inside U. This is UT means fixed locus of U. Yeah. So this is the statement of torus localization. Let me stop here.
Thank you, Professor Oh. Any questions in the audience? There are no questions?
Sorry,
Uh,
I get this, so the nominator is square root V of what, then of L.
The numerator is square root of a virtual normal bundle of L map. So we have a map from firstly we have map from L to M, right? Which is Lagrangian, and M is inside U. So we assume M is local. So this is so L to U is virtual normal bundle from L to U. In the numerator is fixed locus virtual normal. No, just normal bundle of the fixed locus.
Let's say torus is trivial root and still there's a. Should there be like torus fixed part
So
somewhere?
if we start with the -2 symplectic case, then for instance, so this becomes just point. The action is trivial, which is also because we are considering -2 simplex case for this object. And here we have a so what we've seen is this one goes to virtual structure over LT, and here one goes to virtual structure over M. And the localization theorem says this by multiplying. This equals this. After push forward.
So I think Yao is asking whether you have to put the moving part in
Moving
the,
part.
the denominator L.
Yeah, moving part this thing. Yeah. So that I'm already maybe. Yeah. In my mind, normal bond is moving and yeah.
But that's like for
This is the
normal
L. Right. Thank you. Any other questions? Now let's thank Professor Oi to